Okay, so as in the last video we have discussed about the angles between the electric field intensity and the small element of vector area. Since we know that electric flux is the dot product of the electric field intensity and the small element of vector area, when we were removing the dot which was placed between these two vector quantities, we were having cos theta function. Alright, means we have to get the angles, and angles between what? Angles between electric field intensity and the small element of vector area. In today's video we are going to calculate the electric flux due to a point charge which is placed at the center of a circle. So what we are going to discuss today is, we are going to calculate electric flux due to a point charge placed at a center of a circle, placed at a center of the circle. Alright, calculating the electric flux due to a point charge which is placed at the center of the circle. So today we have our topic. So we know that electric flux is basically the dot product of electric field intensity. Electric flux is basically the dot product of electric field intensity and the small element of vector area. Alright, this we have learned in very detail. It is the dot product of electric field intensity and the small element of vector area. Since we know that electric flux is what? It is number of electric line of forces which are passing through a very small element of vector area, which is what we call the electric flux. So electric flux was the dot product of electric field intensity and the small element of vector area. Now the surface is divided. Now we are going to divide the surface, alright, divided into small element of vector vector area. Alright, so now the surface is divided into small element of vector area. Then the flux, what will be the effect on the flux? The flux over the whole surface is given by it is given by what then? Wait, let me highlight this point first, which is very important. Now we are going to divide the surface into small element of vector area. Then the flux will be, as we know that flux is what? Flux is basically the product of electric field intensity and the small element of vector area. We have divided the area into very small surface. Alright, so the area throughout the whole surface would be electric field intensity into summation of small element of vector area. This is basically summation. Alright, so now as when we were calculating the electric field intensity due to an isolated point charge, we got that electric field intensity is equal to kq over r square. E is equal to kq over r square, and this we got to know when we were calculating the electric field intensity due to an isolated point charge. Due to an isolated point charge. due to an isolated point charge. Alright. So due to an isolated point charge, the electric field intensity we get was kq over r square. So substituting the value of electric field into this formula. Alright. Substituting k's value. Let's substitute the k's value. Alright. So phi, which is a symbol of denoting the electric flux, is equal to, instead of electric field intensity, I can write kq over r square and the summation of small element of vector area. Alright, small element of vector area. Wait, let me highlight this as well now. These are very important points. So now, instead of writing k, I know that what is k equal to. K is equal to 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught. So substituting the value of k in this equation. So let's substitute the value of k now. So phi is equal to, instead of k, 1 upon 4 pi epsilon naught into q into summation a square. Alright, not a square, however, the small element of vector area. Wait, let me highlight this as well now. Now we know that area is equal to what? Area of circle is equal to 4 pi epsilon naught. So the whole area of the circle is, the whole area of the circle is what? It is 4 pi r square. 4 pi r square, which means summation of del A would be equal to 4 pi r square. So wait, let me highlight this as well. Very important point. This is very important in terms of MCQs. Alright. Like they can ask, what is the area of a circle? You can say that 4 pi r square. Alright. So this is very important in terms of MCQ. So now putting the value or the substituting the value of del r in this formula now. Alright. So let's write phi is equal to 1 upon 4 pi epsilon naught into q into 4 pi r square. Since we are substituting the value of this del A as 4 pi epsilon naught. Alright, now see what is cancelling here. 4 pi cancel with this 4 pi. Alright, we have, you know what, upon k we have r square too. So I just forgot to write that. Yes, here I just forgot to write too. No worries. Okay, so now we have r square as well. Since we know that the electric field intensity was equal to kq over r square. Alright, so r square we have down to. So r square cancel with this r square. Now what we have remaining is phi is equal to q over epsilon naught. Q over epsilon naught. This is the final equation. What is electric flux equal to? It is equal to the ratio of the charge and the epsilon naught, which is permittivity in free space. So the final equation, wait, let me write that here. So this equation shows that electric flux is equal to, charge per unit epsilon naught times the charge of, or the charge enclosed in a circle, enclosed in a circle. So final equation is showing what? Final equation is showing that electric flux is equal to the charge per unit epsilon naught, or it is the ratio of the charge per unit epsilon naught, which is permittivity in free space, times the charge enclosed in a circle, which means Q over epsilon naught, ratio of the charge per unit permittivity in free space. So this was all for today.